In Lesson 3, our goal is to understand rational and irrational numbers. The first thing we have to be able to do is describe what a rational number is. And rational numbers are numbers that can be written as the quotient of two integers. Since the bar in a fraction represents division, every fraction whose numerator and denominator is an integer is a rational number. Any number that could be written as a fraction whose numerator and denominator is an integer is also a rational number. If we look at the root word of rational, it is ratio. And we know that a ratio is a comparison of two numbers, or two quantities, or two integers in this case. Rational numbers can be represented in a variety of different forms. Every single integer, whole number, and natural number is a rational number. It's a rational number because it can be turned into a fraction, just as the definition states. All integers, whole numbers, and natural numbers can be turned into a fraction if they have a denominator of 1. For instance, 3 is a fraction if you put it over 1, such as 3 over 1. Negative 5, which is an integer, is negative 5 over 1. 0 is 0 over 1. And the square root of 25 is a perfect square where its answer is a whole number, such as 5, which is written as a fraction as 5 over 1. Every terminating decimal is a rational number. Terminating decimals are decimals that have an ending place, or you can identify the number based on its place value. So you can write every terminating decimal as a fraction, so you know all terminating decimals are rational numbers. You can use what you know about place value to find the fraction that is equivalent to any terminating decimal. For instance, 0.4 is 4/10, in which you would put 4 over 10 and reduce it to 2 over 5. 0.75 is 75 hundredths, which would be 75 over 100 because you rate it according to its place value, and that reduces to 3/4. 0.386 is 386 thousandths. Because it's in the thousandths place, it'll have a denominator of 1,000, and 386 over 1,000 reduces to 193 over 500. You can even do this with square roots as well. The square root of 16 hundredths is 4/10, because 4/10 squared would give you 16 hundredths. So since your answer is 4/10, it's rational because that can be turned into a fraction with a denominator of 10 and then reduced to 2/5. The next type of number that we know is rational is a repeating decimal, because we know that every repeating decimal can be written as a fraction. From 7th grade, we know that repeating values can be placed over a series of 9s if the entire pattern repeats. But in 8th grade, we expand upon that farther in order to convert repeating decimals that have more than just a repeating pattern. They may have a repeating pattern and some additional digits as well. So the steps you see here tell you to start by letting the repeating value equal x, adjusting the value to where you have one series of the repeating decimal in front of your decimal, and then you adjust your x value by multiplying the same amount of spaces, which in this case 0.3 repeating becomes 3.3 repeating if you multiply both sides by 10. You then would subtract your original value because that has all of the repeating pattern and only the repeating pattern in behind the decimal. And then you subtract. You subtract your original amount from the new amount that you found. 10x minus x equals 9x. And 3.3 repeating minus the 3 repeating leaves you with 3. Now you can solve the equation that remains. When we were converting a repeating decimal in class, we looked at this process in more detail and broke it down into 8 steps. So the steps for converting a repeating decimal to a fraction, with our goal being to get the repeating portion to drop off, is that we set the repeating decimal to x. which is what we've done here in our example. We then expand the repeating pattern so that way we are sure of what is repeating. So in our example here, the only thing that repeats is the 7. We then move the decimal to be behind one series of the repeating pattern. So we want our decimal to look like 87.7 repeating. And in order to do that, we had to multiply the 0.87 with the 7 repeating by 100. So we also multiply our x by 100. We then go back to that original decimal that we expanded. And we move our decimal again to where all of the repeating pattern and only the repeating pattern is left behind the decimal, which means we want our number to look like 8.7 repeating. Because we did have to move our decimal to the right one place from the original number, we multiplied by 10. Now we subtract the results from 4 and 6, meaning 100x minus 10x gives us 90x. And 87.7 repeating minus 8.7 repeating leaves us with 79. Then we solve the one-step equation that remains, meaning we divide 79 by 90, and then reduce that fraction if necessary. These are the steps that we went through in class for converting repeating decimals to a fraction. After going through and identifying the different types of rational numbers, we did a reflection. We said what fraction is equivalent to 5.1? We want to know, is 5.1 a rational number, and explain. We know that 5.1 is read as 5 and 1/10. So that allows us to write that number as 5 and 1/10. That's the same thing as 51/10. We know this number is rational because it can be written as a fraction. We also know it's rational because it was a terminating decimal. During our exploration of numbers, we were looking to see what numbers are not rational. So we were looking at a number like the square root of 2. And the square root of a number that's not a perfect square. So look at the number line below. The number square root of 2 is found between the square root of 1 and the square root of 4. Since the square root of 1 is 1 and the square root of 4 is 2, that means that the square root of 2 must be between what two integers? As we lay this out, we know that the square root of 1 is equal to 1. We're asking about the square root of 2, and we know that the square root of 4 is 2. So since the square root of 2 falls between the square root of 1 and the square root of 4, which are perfect squares, the square root of 2 falls between the whole number 1 and the whole number 2 on the number line. In number 3, it asks us to draw a point on the number line where you would locate 2. And where did you draw the point? So should we draw that square root of 2 closer to 1 or closer to 2? Because there's only a difference of 1 between the square root of 1 and the square root of 2, and a difference of 2 between the square root of 2 and the square root of 4, the square root of 2 is most likely going to be closer to the 1. So our point may be somewhere around here, which means that we might have drawn that point somewhere around 1.3 or maybe even 1.4. For number 4, it's going to ask us to calculate some numbers to the 10th place to help narrow down that location on a number line. It's going to ask us to calculate 1.3 squared. In order to calculate 1.3 squared, we're going to do 1.3 times 1.3, which gives us 1.69. We're then going to calculate 1.4 squared. 1.4 squared means that we'll multiply 1.4 times 1.4, giving us 1.96. We're then going to calculate 1.5 squared, which means that we would multiply 1.5 times 1.5, giving us 2.25. In number 5, we're asked, based on your calculations, draw a point on the number line where you would locate the square root of 2 now. And where did you draw that point? We should notice that the square root of 2 is going to fall somewhere between 1.4 and 1.5 because squaring 1.5 brought us over 2, but 1.4 brought us pretty close to 2, which means that our number might be somewhere around here. Or maybe even closer when you notice the spacing on that number line. Once you narrow it down to the 2 consecutive numbers to the 10th place, you could take it even farther. You can calculate to the 100th place. For instance, 1.41 squared, which means that we'll multiply 1.41 times 1.41. And that leaves us with 1.9881. We then will square 1.42, which means that we would multiply 1.42 times 1.42. We then get 2.0164. We're then asked, based on these calculations, the square root of 2 is between which 2 decimals. So now to the hundredths place, we know that 1.42 is too much, but 1.41 is not enough. So it's going to be somewhere between 1.41 and 1.42. In number 8, we're going to kind of wrap up some things that we found out in steps 2 through 7. It says that you can continue to estimate getting closer and closer to the value of 2. For example, when you square 1.414, you get 1.999396. And when you square 1.415, you get 2.002225. But you will never find a terminating decimal that multiplied by itself equals 2. The decimal will also never have a repeating pattern. So the square root of 2 cannot be expressed as a terminating or repeating decimal. So it cannot be written as a fraction, which means that numbers like the square root of 2 and the square root of 5, which are not perfect squares, are not rational. You can only estimate their values. They are called irrational numbers. Here, irrational means cannot be set as a ratio or cannot be written as a fraction. So the set of rational and irrational numbers together makes up the set of real numbers, because even though it does not terminate and it does not repeat, it does have a place on the number line. Now we're asked to try a problem. It says the value of pi is a decimal that does not repeat and does not terminate. Is it rational or irrational? And explain. If pi does not repeat and does not terminate, it's irrational. And therefore can only be estimated. Next, we're going to talk about it, and we have some guided practice. It says that you can eliminate the value of an irrational number like the square root of 5 and locate the value on a number line. First, we want to know that the square root of 5 is between which two integers and explain your reasoning. In order to find this, we'll compare it to its perfect squares. The square root of 5 falls between the square root of 4, which is 2, and the square root of 9, which is 3, which means that the square root of 5 is between 2 and 3. We should notice that 5 is closer to 4, therefore we might assume that it is closer to 2 than to 3. In number 11, it says that we're going to mark a point at an approximate location for the square root of 5 on a number line below. The square root of 5 is between which two decimals to the tenths place? So since we think it's closer to 2, we might try squaring 2.2. And when you square 2.2, you get 4.84. Which might not be big enough, so we could try 2.3 squared, which is 5.29. That is too much, so that means that our decimal for the square root of 5 should be between 2.2 and 2.3. So I might place that here on the number line. But we can narrow it down even farther by taking it out to the hundredths place. If I were to square 2.22 squared, I would come up with 4.9284. If I were to square 2.23 squared, I would come up with 4.9729. If I were to square 2.24 squared, and that is a typo in the book, it should say squared, I would come up with 5.0176. So based on these results, the square root of 5 is between which two decimals to the hundredths place? Well, 2.24 squared takes us over 5, but 2.23 squared takes us close to 5. So we would say that it is between 2.23 and 2.24. We then want to draw a number line from 2.2 to 2.3. Label tick marks at hundredths to show 2.21, 2.22, 2.23, and so on. And then mark a point at the approximate location of the square root of 5 to the thousandths place. We know that on the number line we have now isolated the square root of 5 to be between 2.23 and 2.24. If we want to take that out to the thousandths place, we could say 2.31, or I'm sorry, 2.231 squared, and that gives us 4.977361. We know that now we could try 2.232 squared, which gets us a little closer at 4.981824. We could now try 2.233 squared, which gets us to 4.986289. We could try 2.234 squared, which brings us to 4.990756. We could try 2.235 squared, which takes us to 4.995225. We could still try even farther to 2.236 squared, which takes us to 4.99696. We could try 2.237 squared, which brings us to 5.00 4169. That meant that we should be at about 2.236 squared for the square root of 5, because once we got to 2.237, we had now gone over 5. We're then told to try it another way. Explore using a calculator to estimate irrational numbers. We're told to put the square root of 5 on our calculator and see what we get. And we come up with 2.236,067,978. So if this number is equal to the square root of 5, then the number squared should equal 5. Now we're told to clear our calculator and then enter that result from problem 14, which was 2.236067978, and then square it. The result that we get is 5.0000000002. If we explain this result, we might say something along the lines that the square root of 5 is only an estimate. Because it's irrational. And that means that we could get close to 5, but not exactly 5. As we make some connections, we're asked to show that 0.74 repeating is equivalent to a fraction. And then we want to know, is 0.74 repeating a rational or irrational number, and explain. If we follow the steps that we went through in class, we know we'll first take 0.74 repeating and set it equal to x. We'll then expand the pattern to where we recognize that x is equal to 0.747474. We're going to move the decimal to where one series of the repeating pattern is in front of the decimal, meaning our number will now look like 74.74 repeating. In order for that to happen, we had to move our decimal 2 places to the right, which is equivalent to multiplying by 100. We then are going to go back to our original number and have all of the repeating pattern and only the repeating pattern left behind the decimal. That means it's going to look like its original form, 0.74 repeating. In order to make our decimal look like that, we didn't have to move the decimal at all, so this is just x. We now subtract our results, and 100x minus x leaves us with 99x. Our repeating pattern now drops off and we're left with 74. So we'll divide 99 to solve the one-step equation, and then we're left with x is equal to 74/99. We would reduce this if it was necessary. Because 0.74 repeating can be turned into a fraction, it is a rational number. In number 19, we're asked to analyze. It says a circle has a circumference of 3 pi inches. Is it possible to state the exact length of the circumference as a decimal and explain? The answer here is no, because pi is irrational. And it's still irrational even if you multiply it by 3. Which means you can't get the exact length, you could only get an estimate. In number 20, we're asked to draw a Venn diagram showing the relationship among the following sets of numbers: integers, irrational numbers, natural numbers, rational numbers, real numbers, and whole numbers. We know that regardless whether the number is rational or irrational, it fits into the category of the fact that it's a real number. And it's real because it's got a spot on the number line. Within real numbers, we have two categories. The first category is irrational. And irrational is the opposite of rational. Rational numbers are all numbers that can be placed as a fraction. Within rational numbers, we drop down to integers. And integers contain the positive and negative whole numbers, meaning all the way from negative infinity to positive infinity. Just below integers are whole numbers. And whole numbers include all of the numbers from 0 to infinity. And the smallest subset of numbers is natural numbers. And natural numbers are called counting numbers. They only go from 1 to infinity. Overall, from this lesson, you should be able to identify the difference between rational and irrational numbers. If a number is rational and you see it as its decimal form, it's going to terminate or stop or have a repeating pattern that can be converted into a fraction. If a number is not rational, but it can be placed on a number line, then it is considered irrational. Irrational numbers are always in a decimal form, and they never terminate, and they also never repeat.